Welcome to Unit 9, Lesson 2, where we'll be talking about using transformations to graph quadratics. So far we've been using standard form, but in this lesson we're going to use a very basic version of transformation form. This transformation form is really standard form without the b term. We're going to learn how A scales the graph and how C shifts the graph up and down. I want to make sure that you understand that this is a very simplified form of transformation form, and in Algebra 2 you'll learn a little bit more advanced of a form where we can also shift the graph left and right. We're going to start things off by focusing on C. Using what we know about standard form, let's go ahead and graph y equals x squared. Now I'm not showing you the process, but I'm going to tell you it would generate these points, which would give us the following graph. This equation y equals x squared is known as a parent function. It's the most basic quadratic possible. There's no number in front of x squared, and there's no numbers after x squared. So we're really just looking at the basic y equals x squared parent function. Now let's take a look and see what this 2 does when we add it to the second equation. Using the same methods, you'll see that the y values all went up by 2. And now let's throw that graph on here. And when we take a look at this graph, you'll see that all of the points from the parent function shifted up 2 units. So that positive c shifted the graph up c units, in this case 2. Now let's take a look at this third graph and see what this minus 1 does. Well, when I throw that on the grid, I see that that original parent function shifted down 1 unit. So a negative c shifts the graph down c units. So what we learned here is that c is going to impact the graph by shifting the original parent function up or down c units. Now let's focus on a. Well, from last problem, we already know what the parent function looks like. So let's get that on the graph and take a look now at y equals 1/2 x squared. So what does this 1/2 in front of the x squared do? Well, as I graph these points, we realize that this graph gets a little wider than the original graph. Well, now let's take a look at what happens when we have a 2 in front. Well, with that 2 in front, we see that the graph gets a little narrower than the original parent function. Finally, let's take a look at what this negative in the front does. Well, this negative flipped the whole graph upside down. So let's summarize what we learned here. If a is between 0 and 1, so something like 1/2, we notice that the graph got wider than the original parent function. If a is greater than 1, like 2, we notice that the graph got narrower than the parent function. And if a is negative, like this negative sign in front of x squared, which is really a -1, the graph flips upside down, which is also known as reflecting over the x-axis. So putting those last two concepts together, we see that C is going to shift the graph up and down, and A is going to scale the graph, meaning make it wider or narrower. Now in a moment we're going to put those ideas together and start doing some problems, but before that I want to talk about zeros. The x-intercepts of a quadratic function are also known as the zeros of that function. So what we're talking about are these spots where the graph crosses the x-axis. These are really important as they actually line up with the answers to the equation 0 equals ax squared plus bx plus c. And as you'll see throughout our examples, a quadratic function can have 2, 1, or no zeros, depending on how it's positioned. This is something we're going to get into more depth with later, but we're going to start that today. So now we're going to get into some examples that put everything together. The first thing they're going to say is consider the parent function and tell us how some other graph has affected that original parent function. What transformation has occurred? Well, for this problem, we have a c value of -5. So we'll be saying that the graph shifts down because it's negative, 5 units. Now for the second question, they're giving us a really similar equation and asking us to draw a rough sketch. That means you don't need accurate points, you just need the right kind of picture. Well, again, this -4 means that we're going to shift down 4 units. Well, to draw a rough sketch, the first thing we're going to do is draw our parent function. I'm drawing this dotted so that it's clear that it's not part of the actual graph. Now I'm going to do a little notability trick here to make this an easier visual. I'm going to draw my final graph on top of y equals x squared and then show the shift happening. Since the graph is shifting down 4 units, I'm just going to take this original graph and shift it down. Now we're not labeling our axes, so it doesn't really matter exactly how far you shift down as long as you're showing that you're shifting down below the original graph. And this is enough to say that I've drawn a rough sketch. You don't need to do the notability trick of sliding it down. You could have just drawn that graph from the beginning. Now this last question asks us, how many zeros does this function have? And all it's really saying is, how many times does it cross the x-axis? Well, we see it cross once and twice, so it has 2 zeros. That's all it's asking, is how many x-intercepts, how many times does it cross the x-axis. Now remember, this was a negative c value, which is why we shifted down. If it was a positive c, we would have just drawn it somewhere above the original graph, like that. And this problem's over. Now again, this next problem starts off by asking us to explain the transformation from the parent to a new graph y equals 3x squared. Well, this 3 is greater than 1, which we learned earlier means it's going to make the graph narrower. So that's what I'll communicate. Now again, for my rough sketch, I'll start off with that parent graph. This is the rough sketch of y equals x squared. And since we're getting narrower, I'll just draw my graph with the same vertex, narrower than that original graph. And that's it. There's our rough sketch. I've shown that the new graph will be narrower than the parent function. And now they ask how many zeros? Well, I'm hitting the x-axis in one spot, so there is 1 0. And that's it. Now this next one has a few things going on. Again, we're asked to explain the transformation from the parent. We see this -3, which means the graph is shifting down 3. And we see this negative sign in front of x squared, which says the graph is flipping over. We always start with the scalar first when we're doing the transformation. So we're going to say first that the graph will be flipped, and then that the graph will shift down 3 units. So this one's going to take a couple of steps to draw the rough sketch, because we have a couple of things to do. The first thing I'm going to do, and again I'm going to dot this so that I know it's not my final answer here, not actually part of the graph, I'm going to draw the graph getting flipped over. So that's my first step. Now I'm going to draw the graph being shifted down 3. So it's going to be lower than it was originally, so I'll take the vertex and slide it down somewhere. There's no scale to this graph, so you don't have to be perfectly accurate. It just has to be below where the x-axis is. And then I'm going to draw a similar shaped graph, and that blue graph will be my final answer. And since I've made the curve solid and not dotted, it communicates that this is my final answer and part of the actual graph. Now, you'll notice for this graph that we start below the x-axis and we're trending downward. We're never coming back up. So this graph actually has no zeros. It's never going to hit the x-axis. So I write down that it has no zeros, and this problem's over. All right, and moving on to another example. Again, we're being asked to explain the transformation from the parent function y equals x squared to this new function. Just like the last problem, we're going to talk about the scalar first, and since 1/2 is smaller than 1 and larger than 0, it's going to make the graph wider. And then this +2 is going to tell us that the graph is going to shift up 2. And now we've explained the transformation. Just like how we explained our transformation in 2 steps, we're going to draw this in 2 steps. The first step is going to be making the graph wider. So I'm going to draw a wider graph, and again I'm going to make it a dotted curve since it's not part of my final answer, and then I'm going to shift the graph up 2 units, which just needs to show that the graph is moving upward. And this wider graph shifted up 2 units is our final graph. Now again, this graph starts above the x-axis and only goes upward, so it's never going to hit the x-axis, meaning it has no zeros. And this problem is finished. Now in this final problem, all we're going to do is use what we've learned to be able to match some equations with some graphs. Our first equation is negative, so the graph should be opening downward, which rules out A, D, and E. Now this graph shouldn't be shifted at all as there's no C over here. And in letter C, you see that the graph starts above the x-axis. In F, you see it starts below, so it's been shifted up or down. Where B starts at the origin, which means it hasn't shifted at all. And that's what we were looking for. So our first answer is going to be B. Now for this next one, we have a positive graph, and we're shifted up 5. So it shouldn't be one of the graphs that open down, and we should see it start above the x-axis, which is what we see happening here in D, making D our answer. For this next equation, we're negative and shifted down, meaning below the x-axis. So negative rules out A and E. C starts above, so it was shifted up, where F's vertex is below the x-axis, meaning it was shifted down, and that's what we were looking for. Finally, this last equation again opens down, which rules out A and E, and it starts above the x-axis, which confirms for us that this should be C, making C our final answer. All we did here was used our knowledge about how transformations would move the graph and what general rough sketch we should be looking for, and we were able to rule out different options and come up with the right graph for each problem. To summarize this lesson, Every equation in this lesson has two potential transformations. One involves the A term, which can make the parent graph narrower or wider, or flip it. The other is the C, which can shift the parent graph up or down. If you came away with anything else, write that down now. Otherwise, we'll see you in the next lesson.